Welcome, everyone. If you've ever looked at an autonomous robot and wondered, how exactly does it translate raw sensor data into intelligent movement? Well, you are in the exact right place. In this explainer, we're going to completely demystify ROS2, the robot operating system. And we aren't just going to be talking in abstract theory either. We are literally going to build up the architecture of a functioning autonomous surveillance robot from scratch. Think of this as a focused, developer-level training session to give you a rock-solid foundation in modern robotic software.
Okay, let's look at our roadmap for today. We're going to hit 6 key areas: the brain of ROS2, nodes, topics, the publisher-subscriber model, services and actions. And finally, we'll tie it all together with a complete system flow. Section 1, the brain of ROS2. To understand how our robot thinks, we really need to figure out where its brain actually lives in the tech stack.
Think about a robot's technology stack from the bottom up. Down at the bottom, you have your physical hardware, right? Your motors, your cameras, the LiDAR sensors. On top of that, you usually have an operating system like Ubuntu. And right there in the middle sits ROS2 Humble. Above ROS2 is where your actual application code lives. Now, the huge takeaway here for you as a robotics developer is that you almost never write code that talks directly to the hardware. ROS2 handles all that messy hardware complexity for you.
So ROS2 acts as what we call communication middleware. It's essentially a highly efficient postal network for your robot's data. It provides these invisible plumbing pipes that let your software components safely and reliably exchange information, which brings us perfectly to the individual houses that make up that network. Moving into Section 2, nodes as the working units. Let's dig into how the actual computing work gets done. In the ROS2 universe, the core processing unit is called a node. You can think of a node like a highly specialized worker on a factory assembly line. It is a completely separate executable process, and it follows a really strict single responsibility principle. It only does one job, just one, but it does it incredibly well. To put that into perspective, in our custom surveillance robot, we absolutely do not have one massive monolithic block of code running everything. Instead, we have 4 distinct Python nodes. You have the YOLO node that watches the camera to detect suspicious activity. You have an A-star planner node that strictly calculates the route, a path smoother node that turns that jagged route into a clean curve, and a smart path controller that steers the wheels. They are completely independent, meaning if you want to swap out your smoothing algorithm a year from now, you literally only have to change one file. It's brilliant. Section 3, topics, the data channels. Now, this naturally raises a massive architectural question. If these workers are totally isolated, how do they talk to each other? Well, they use topics. Imagine topics as dedicated radio frequencies that any node can broadcast on or tune into. Every single topic has a unique name that always starts with a /, like /CMDVEL for velocity commands. They also enforce strict message types. This is super important because it ensures a node expecting a simple XY coordinate doesn't accidentally receive a massive, uncompressed raw image file. Plus, this communication is fully asynchronous. The publisher just shouts the data out into the void. It doesn't wait around to see if anyone is listening. To put it simply and really lock this concept in, the nodes are the engines. They do the heavy lifting, the computing, the deciding. The topics are the highways, transporting the cargo between those engines. Section 4, the publisher-subscriber model. Let's see how the data actually gets onto those highways. If you've used older systems like ROS1, you might remember needing a centralized master process to coordinate everything. Well, not anymore. ROS2 uses an industry-standard data distribution service, or DDS. It is entirely decentralized. Node A can publish to a topic, while Node B and Node D independently subscribe to it. The nodes dynamically discover each other on the network all by themselves. It's basically magic. If one node crashes, the rest of the network just keeps on communicating seamlessly. Let's trace a real message through our surveillance pipeline. Say our YOLO node spots someone loitering for over 5 seconds. Highly suspicious. The YOLO node instantly constructs a pose-stamped coordinate message and publishes it right to the goalpost topic. Meanwhile, the planner node, which has just been quietly subscribed to that exact topic, receives those coordinates instantly and wakes up to map a route. Notice something there? The YOLO node and the planner node never actually talked directly to each other. The topic facilitated the whole thing.
Section 5, Services and Actions.
The publisher-subscriber model is incredible for continuous streams of data. But what if your robot needs to do something a little different?
Yeah, sometimes you just need to force a node to do something specific right now. That is where services and actions come into play. If you have a quick one-off request, like, say, telling the robot to clear its map right this second, you use a service. Services are synchronous. The system pauses and waits for a reply. But on the other hand, actions are for complex, multi-step tasks. Navigating across an entire building takes time, right? So you'd use an action. It gives you continuous progress feedback, and crucially, it allows you to cancel the request midway through if an emergency happens. Section 6, the complete system flow. Okay, we have our building blocks. Let's wire this whole robotic brain together and watch it work. Picture the entire autonomous surveillance pipeline cascading from top to bottom. Up at the top, our simulation pushes raw camera frames via a topic down to the YOLO node. The YOLO node crunches the pixels, makes a decision, and publishes a target down to the planner. That path data flows into the smoother, down into the smart path controller, and finally out as a command velocity message that physically spins the robot's wheels. And while all this is happening, the robot's localization data is constantly looping back up the chain to keep the driving perfectly accurate. It is just a beautiful modular flow of data. Now, as a real engineer, you don't just stare at the physical robot hoping it works. You have to inspect the matrix. Jump into your terminal. If you type ROS2 topic echo /cmdval, you can literally watch the math updating in real time as the robot turns. Or, even better, run RQT graph. It automatically generates a live visual map of every single node and topic running on your system. This is how you actually debug and master ROS2. By making these invisible data streams visible. By breaking down ROS2 into these core concepts, the middleware, the specialized nodes, the topic highways, services, and actions, the magic of robotics just becomes a structured, totally solvable engineering puzzle. We've just traced an entire architecture from a raw camera pixel down to a rotating wheel. So with these foundational dev tools now firmly in your toolkit, what ambitious autonomous system are you going to build next?